All right, today we're going to be talking about proofs dealing with reflections. Typically these all go about the same way. What you have to start with is by reflecting all the points, and then you reflect the figure, and then we can say the figures are congruent. So one of the keys to know is anytime that it says that there's a perpendicular bisector involved, if you think what that's really saying, if this is the perpendicular bisector of that this has created equal length and these are 90-degree angles because it's right in the middle and then those 90 degrees from the perpendicular. Well, that's really what our definition of reflection is, that this is equal distance from this, creating that 90-degree angle in between. So that's kind of the main idea here. So we'll start as we do with every single proof and we'll do our given. So BD is the perpendicular bisector of AC, and that's our given. Our second step then is to reflect all the points over that line. Once I've reflected all the points, then I can reflect the figure. So I'm going to say the reflection over BD of A is C. That gets to happen because of here. Now, I'm also going to reflect the other points because I'm going to look at this as one triangle and two triangles. So I'm going to say the reflection over BD of D is itself, so is D, and the reflection over BD of B is B. Those we get to say because they reflect over the line that they're on, so obviously they are themselves. This is all due to the definition of reflection. Okay, so I have reflected each individual point. Now, if I know that, sorry, it's kind of hard to see up here. If I know that B becomes B, A becomes C, and D becomes D, that means this triangle must have reflected to become that. So that's what we are going to put on there. So we are going to say that the reflection over BD of triangle ABD is triangle CBD. Now you're going to see, depending on what notes you look at, different teachers call this different things. We are going to call it figure reflection theorem. Figure transformation theorem. That's what the other teachers call it, figure transformation theorem. And some call it figure reflection theorem, and I'm okay if you do that if you would prefer to put the word reflection there, because a reflection is just a type of transformation, so in some sense that's a little more specific. Okay, so if I have reflected the figures, I am saying that this has become this. Now I can say that they are congruent, because my ultimate goal in this one was to say that I have side lengths that are congruent. It should look like that. So I want to say that the figures are congruent first. So I'm going to say that triangle ABD is congruent to triangle CBD, and that's definition of congruence. Remember, definition of congruence is when we're talking a figure. We'd have segment congruent theorem if we're talking a segment, or angle congruent theorem if we're talking an angle. But right here we're talking an actual figure, so we'll go with that. Now that I have proven that the triangles are congruent, then I can prove that the angles are, that the side lengths are congruent, which is what I wanted to. So I'm going to say BC is congruent to BA. And that's because of CPCF, which was congruent parts of congruent figures. These are both parts of the triangle, so if the triangles are congruent, their parts must be congruent. Almost every single one of these with reflections follows this exact same format. Sometimes you don't end with CPCF if it just wants to know that the figures are congruent, but it always goes, the given, you need to reflect the points individually, and that's always definition of reflection. Then you need to reflect the figures once all the points have been reflected. Then I can say those figures are congruent, and then if need be, go to CPCF.